Here we go, worksheet 1215, AB number 6, multiple choice packet. We're going to explore limits, continuity, L'Hopital's rule, asymptotes, symmetry. So a bunch of stuff that's kind of related to limits. It's good to have a really good understanding of these. You're going to get questions on multiple choice for sure that just ask you some of these questions. So limit is this idea, kind of draw a picture here that goes with it. We have some curve and we're approaching some point A, and whatever value that both sides are approaching, it's got to be both sides, then that's the limit. Okay. Now, there could even be a hole there. If there's a hole, discontinuous, does the limit still exist? A hole or a jump or something like that? Does the limit still exist? Yes. So the function doesn't have to agree with what's the left hand sides are going towards. So it says we're getting closer. So yes. Continuity, kind of a simple way of sort of describing what it is. Very non-technical. Do not use this on free response. You can draw a graph without lifting your pencil. So, otherwise, something that would cause you to lift your pencil would be a hole. Okay, and it's not enough to be, I can trace around the hole and still go. No, you understand. Hole technically doesn't have a border. We just draw it like that. So there could be a hole, which is and then we could have a jump like that. Or we could have a vertical asymptote of some kind. So those are types of discontinuities. The three main types. So these are discontinuities. Okay. Now, if f of x is continuous at some point x equals a on a function, then what has to be true is that the value of the function has to equal what the limit is as we approach that value. Okay, so the y value at that point has to agree with the limit. The limit doesn't need to agree with it for the limit to exist, but if the limit exists and the point is what the limit is going to, then that must mean it's all connected. There's no way that you have a jump or a hole or something. So that's called the definition of continuity, and sometimes you're required to use that on free response problems. You have to you have to show that the left side limit equals the right side limit, so the overall limit exists, what it is, and then you got to show me what the value of the function is, and then you got to show me the degree, and then you can tell me that the function is continuous by the definition of continuity. Differentiability means that the derivative exists everywhere. Now, for the derivative to exist, that means that the slopes on both sides agree with each other. But there can't be a hole or a jump or something like that there. So it has to be continuous. So you can't, no hole, no jump, no vertical asymptotes. Okay. So some examples of non-differentiable curves that are continuous. So continuous but non-differentiable would be something like this. So these are reasons that even if both sides agreed, slope, it still wouldn't be differentiable because there's a hole or something. So a cusp, a corner, which are very similar to each other, or even a vertical tangent. So usually it means a differentiable curve is a smooth curve, but this is a smooth curve that's not differentiable at that point. Now it's differentiable at all the other points, but not there. So here's a classic problem. I think we've already seen this come up, and I've given to you a lot this year. I give you a piecewise function, and piecewise functions are good because something interesting is happening where the two pieces start and the other one begins. Are they connected? Is it continuous, or is it smooth connection? So the y values have to be, for it to be continuous, the y values have to be the same, which means that the graph, the two pieces connect to each other. And so we could say, all right, well, let's plug F1 in there, and we get 2 and get 2, and they're both equal. So, yep, this is continuous. Differentiable says that the derivatives match, the slopes match from both sides. But it does require continuity first. So if you're ever going to check for differentiability, you got to check continuity first. So we would take the derivative of the piecewise function, say, all right, 2x plus 1 and 2, this is for x is greater than 1, and this is for x is less than 1. Even though this says less than or equal to, we can't say that or equal to yet, because if it's not differentiable, if they don't agree, then a derivative doesn't exist there. So then this is the lazy way, by the way, of doing this. So we plug 1 in, we get 3, we get 2, they don't equal each other. Therefore, it's not differentiable at x equals 1, and therefore the derivatives, these are the derivatives piecewise, but at x equals 1, there is no derivative. So it's not differentiable. It is continuous. It's not both, and it's not neither. There's one answer on here that by itself would be illogical. So which answer would make sense as its only lone answer? That would be B, right? You can't be differentiable only and not continuous. So if it's differentiable, that implies that it is continuous, right? So if it's differentiable, it's going to be both. So answer B doesn't make sense on its own. I want you guys to try a few problems. These should be pretty quick. I want you to try 1, 2, and 3. So pause the video. Give yourself a chance to try these and see how you do, and then I'll show you how to do them, and then we can keep going. So the first one says, for which of the following does the limit as x approach 4 exist? So as long as both sides agree, which this one does, as long as both sides agree, which this one does, it's okay if there's a jump, it's okay if there's a hole. This one, they don't agree. So it's got to be 1 and 2. Number 2, the graph of the function f, whose domain is the closed interval 1 to 7, is shown below, which is the following statements about f of x is true. The limit as x approaches 3 equals 1. Now, the limit as x approaches 3 is actually 3. The value of the function at 3 is 1, but that's different than the limit. Limit as x approaches 4 on both sides is 3. Now, on one side it's 3, and the other side it's like 1.5. So that doesn't work. F of x continuous at 3? Nope, there's a hole, a jump. F of x continuous at 5? Yes, that looks like a solid dot, right? And does limit as x approach 6 equal f of 6? Now, this is the definition of continuity, by the way. And what it's saying is, as we approach 6, first of all, limit doesn't even exist at 6, so this doesn't even exist. So how's that? So the answer is D. Number 3, the graph of the function f is shown below, which the following statements about f is false. So be careful. Sometimes they're asking for true, sometimes they're asking for false. I think a lot of times we might be tempted to pick true if we're not paying attention. So f is continuous at A. No, there's a jump. F has a relative maximum at A. It doesn't seem like it. X equals A is in the domain of the function. Yes, it is, because it's defined, even if there's a jump. Now, we're looking for the one that's false. So far, the first two seem false. D, the limit as you approach A from the right side is the same as S approaches A from the left side. Yes. The limit as x approaches A in general exists. Yes, that would mean the two sides agree. Now, F is definitely not continuous at A, and it doesn't seem like it has a relative max. Like we usually think of a peak, right? But really, technically, a relative max is a value on the graph that is definitely bigger than the immediate values on the left and right. So there actually is a relative max. And by the way, the derivative is undefined, so it's a critical point. So the one that is false is A. Okay, we're going to go to the next page. And let's take some notes about L'Hopital's rule. Now, I really want you to pay attention to this because I'm going to tell you some stuff that you need to make sure you do on free response to get credit for this. But in general, if you plug, say, -3 in, so the first step of trying to evaluate limits is called substitution. You just plug the value in. So you get a +9 minus 18 plus 9 is 0, -3 plus 3 is 0. And we call this an indeterminate form. And that means that we cannot determine the answer. It might be 0, it might be undefined, it might be 3. So back in pre-calculus, what we would do sometimes is if we got 0, 0, there might be a hole in the graph. So we would factor the top and the bottom. If there's a hole in the graph, what happens is you get a common factor in the top and the bottom, and you can cancel them out and then plug -3 in here and we get 0, and that actually is the answer. The reason this is okay is because even though this looks like a crazy rational function that you would expect to have like a vertical asymptote at -3, it actually behaves like this line, right? Because the top and bottom both have this extra number that cancels itself out no matter what x is, and you're left with this. So this is really a line with a y-intercept of 3 and a slope of 3 up 3 over a slope of 1 up 1 over 1 up 1 over 1 down 1 over 1 down 1 over 1 down 1 over 1. So this is what that line looks like. This is what this function looks like with one little thing. We still, even though this reduces down to that, we still can't ignore that it was in the denominator originally, and x equals -3 is off limits. So here's x equals -3, so there's a hole in the graph, right? So because it is a line with a hole in it. So that's why we can actually take the limit of the line, even though the line doesn't have a value there, both sides agree and do tell you what the limit is. So that's relevant sometimes. So just going into another problem similar to this, we get 8 minus 8 is 0 over 0. And so we could try and look for the hole. Now, if you get infinity over infinity, that's a different issue. That's not a hole. That's in behavior. But we could do you guys remember how to factor this? Make your Algebra 2 teacher proud. It's the difference of cubes. The difference of cubes is it's something cubed minus something cubed. So it's going to be x minus 2. And then there's going to be a trinomial. It's going to be x squared and the first thing squared. So the first thing that was cubed on its own, second thing is cubed on its own, and then the first thing that was cubed squared now, second thing that was cubed squared. And in the middle, you multiply them times each other, and then use that SOAP, same, opposite, always positive, over x minus 2. Now, of course, you could use synthetic division. You wouldn't have to use rational root theorem because you already know that x equals 2 is the root that is making the top go to 0. So it's a little easier. You could do synthetic division if you got something that wasn't even factorable. So now if we plug 2 into what's left, we get 4 plus 4 plus 4 is 12. So the answer ends up being 12. Now, either what if you don't remember how to factor it? What if it's something you can't factor? There's another approach called L'Hopital's rule. And what it technically says is if the limit of the top equals the limit of the bottom, both equals 0, then the limit of the top and bottom directly equals a new limit of the derivative of the top and the derivative of the bottom separately. Don't do quotient rule, which is good because quotient rule would be terribly messy, but it is also just completely wrong. So no quotient rule, just doing the derivative of the top, derivative of the bottom. Okay, so derivative of the top over the derivative of the bottom. Now, this also works if you get infinity over infinity. Okay, that's the other indeterminate form. Now, this is like the way you would need to show it on the AP test if you wanted to get credit for L'Hopital's rule. So I'll show you in a second. So let's say this is a problem you got, and you just tried it at first. You got 0 over 0. You say, okay, well that's a now on multiple choice. I would just be like, oh, okay, that equals limit as x approaches 2 of the derivative of the top over the derivative of the bottom, plug 2 in, and we get 12. And by the way, this is the same problem we just did up here. So that was actually, I think, easier. Now that's fine. That's the very lazy way. This is not good enough for free response. Free response, you would do this maybe, and that one you wouldn't want to do that. So for FRQ, after you did this, you would say, oh, okay, well, this is what you'd say. You say since x, you could say since limit as x goes to 2 of x cubed minus 8 equals the limit as x goes to 2 of x minus 2, and since they both equal 0, we may apply L'Hopital's rule. You got to name it. But you also got to set up why you're allowed to use it. And this is the way. This isn't good enough. That's lazy. It's not technically. This is the technical way. Okay? L'Hopital's rule. And then what you do is you say, okay, you don't just jump to the limit of the derivatives. You have to say the limit as x approaches 2 of the original expression equals the limit as x approaches 2 of the derivative 3x squared over 1, and then you would finally get 12 for the answer. So on a FRQ, this is the work you have to show to get the credit for L'Hopital's rule. You got to say you're using L'Hopital's rule. You got to say why L'Hopital's rule works, and that's not good enough. And then you got to say when you use L'Hopital's rule that the original limit directly equals the new limit. There shouldn't be a break or 0, 0 in between. That's not technically correct. So just a heads up. Okay, let's see. Let's look at number 8. Says f of x, fx equals this is continuous. So then what's the value of f negative 3? Now, your first thought is probably, well, let's plug 3 in. And we get 9 minus 9 over negative 3 plus 3 equals 0 over 0. So is it 0? Is it undefined? This is a limit issue. So the value of the function, technically right now, there's probably like a hole in the graph, right? So like the limit as x approaches negative 3 of x squared minus 9 equals x plus 3 gives you 0 over 0. Now I'm being lazy, so I'm going directly limit as x approaches negative 3 of the derivative of the top and bottom. Or you could do the whole. You could do x plus 3, x minus 3, which only works for the 0 ones. Or you could do L'Hopital's rule. And so we take the limit of the derivative of the top and the derivative of the bottom, and that would also give you negative 6. Now, here's the deal. Currently, this function has a hole in it. It doesn't have vertical asymptote. It has a hole, and this is showing you what's happening on this graph. The graph, looks like this, and then at negative 3, there's a hole right here. Now, both sides are going towards negative 6. And if we leave it the way it is, then it's not continuous. But if it's going to be continuous, what we're going to do is we're going to fix the hole. We're going to say, well, this is what it's defined as, but then at negative 3, it's going to be negative 6. So you can actually plug the hole. You can fix the hole and kind of make it into a piecewise function. Okay, next page, let's talk about asymptotes. So we have 2 different kinds of asymptotes, and they seem very similar to each other, but they come from totally different reasons, and they have totally different issues. So vertical asymptote is caused by division by 0. Okay? And that means the function is not defined, which means that the graph can't exist there at all. So we'll just draw a generic one for our notes. So you might have some vertical asymptote at A, and then maybe the graph goes like this. Maybe the graph goes like this of the function. Okay? But these can never be crossed. Like the function can't go through them because they are undefined. Okay? Now, horizontal asymptote comes from a totally different issue. It comes from the issue of, we call it in behavior. Okay? So we're going to positive, negative, infinity. So we call that in behavior. Okay? And it's a horizontal line. We usually draw them as dash, and then the graph gets closer and closer and closer to it as you go to infinity. Now, it might just be on one side. It might be both sides. Okay? But the thing about these is you can cross them. Okay? So you might have a horizontal asymptote, and it might at first cross it and cross it and cross it and possibly cross it infinite times, but it's eventually getting closer and closer to it. So you can cross a horizontal asymptote and then approach it eventually. So it's really that it's going to go towards it as we go to infinity. Short term, it can cross it. So possible to cross, because it's not undefined issue. Now, how do we? This is an important question because sometimes they ask you to do this. How do we calculate the limit to plus or minus infinity? And that's, by the way, this is the way. If they said if they asked you what is the horizontal asymptote, then you're going to plug infinity and negative infinity. You take the limit as you go to infinity and negative infinity. Now, in this case right here, what we want to do, if we were to plug infinity in here, this is going to be infinity times negative infinity. That's going to be negative infinity. On the bottom, it's going to be positive infinity. And that's an indeterminate form. So we could do L'Hopital's rule, but that could potentially take a lot of work. L'Hopital's rule isn't like a magic shortcut. Sometimes it's a lot easier. Sometimes it isn't. Like here, it would require multiple steps of L'Hopital's rule. Like if you do L'Hopital's rule and you get a 0 for 0 again, then you just got to do it again. The better way usually with infinity is to look for the dominant terms. If you know what terms are the biggest and how they're behaving in relation to each other, you can figure out the answer real quick. So we could FOIL this all out. You could FOIL it all out just to make it easier. Now, I don't really even think I need to. I think the biggest term on the top is going to be negative 3x squared. But just this time, at least to illustrate, you're going to get 6 minus 9x plus 2x is minus 7x minus 3x squared. And on the bottom, we just have x squared plus 5x. And so this is the dominant term, and this is the dominant term. And what I'm going to argue is that all these other ones are negligible as we go to infinity. They really just don't matter. In comparison to these terms, they're like nothing. You're like, but infinity times 5, that's a lot. Yeah, but compared to infinity squared, it's nothing. I'll convince you right now. So now, by the way, these are the dominant terms. So if you compare them to each other, you say, oh, well, these terms are growing at the same rate as each other, so it's going to be negative 3 over 1. And then that would be your answer. But let me just make it that much more obvious why we can ignore those other terms. I wouldn't do this work usually, but I've shown it to you guys before. What we can do is divide out the highest degree term out of the top and the bottom. Like, what's the biggest x to a power in the whole thing? It's x squared. So if we divide that out, so by the way, I call these the dominant terms, and they're the highest degree terms. Okay, they're gonna be the biggest. But if we divide it out, if we divide x squared out, we get 6 over x squared minus 7 over x minus 3. And that's fine to do as long as we do it to the top and the bottom. This is going to be 1 plus 5 over x. Now imagine if we go to infinity. Isn't this going to go to 0? Isn't 6 divided by infinity 0? Isn't 7 divided by infinity 0? Isn't this 0? And guess what's left? Negative 3 over 1 is negative 3. Now, I'm usually not going to go through that effort. I'm just going to be like, oh, negative 3x squared over 1x squared is negative 3 over 1. Now, if the degree of the top is bigger than the highest degree on the bottom, the top's going to blow up, and the whole thing's going to blow up to infinity, which we say diverges, okay, or does not exist. If the bottom has a higher degree, highest term than the top's, then the top's going to outgrow the bottom, and we're going to get a number divided by a much larger number on the bottom, which is going to go to 0. If they're the same degree, then you just get the ratio of the coefficients of those dominant terms. So why don't we try 9 and 10 and 12, 13, and 14. Why not? Let's get a bunch of these done right now. Get your homework done, and then I'll help you out. So try those out. See what you can do. Pause the video. And then after you try them, unpause it. And we'll get those done. In fact, I don't know. We'll just do all of them. Get the whole page done. These can be fast problems. Okay, the first term, if you just look at dominant terms, it's x cubed, it's 4x cubed. They're the same. So it's going to be 1/4. You're done. That's the answer. Okay? Now, if you were to plug infinity in, you would get infinity over infinity, which is the indeterminate form, which we could do L'Hopital's rule. Now, we would have to show a little more work for a free response to get credit for it, but this is the lazy way. Equals the limit as x approaches infinity of, take the derivative of the top, 3x squared minus 4x plus 3 over 12x squared minus 6x plus 2. Plug infinity in. We get infinity, which means we could do L'Hopital's rule again, which we can do, and sometimes that's helpful. This is going to give you 6x minus 4 over 24x minus 6. Plug infinity. We get infinity over infinity again. We're going to do L'Hopital's rule again. Limit as x goes to infinity of 6 over 24, which is 1/4. So it works. I wouldn't do that though, right? So for in behavior, look for the dominant terms. So in this problem right here, the dominant terms are x to the 5th and x to the 6th. It's the exponent on the x's that matters. Now this one's bigger, right? So this is going to 0. Done. Done. Right? That's it. It's going to 0. Let's see. Number 11, going to infinity, dominant terms. Right here, they're the same power, so it's going to be negative 1/4. Done. Right? For which pair of functions f and x below will the limit f of x go to 0? So that means the bottom has to be growing bigger, faster than the top, right? So this is going to be e to the x over x squared. Which one wins? Which one grows faster? This one grows faster. This one's going to go to infinity, so that one's out. This one's e to the x over natural log of x. Sometimes knowing what the graphs look like, e to the x looks like that, right? Natural log of x looks like that. They're both going to infinity, but this one's getting slower and slower. This one's blown up. The e to the x wins. It goes to infinity. Natural log of x over e to the x. Well, this one's going to grow faster, so that's going to go to 0. So I think that one's the answer. Let's just double check the others though. X over natural log of x. Which one is growing faster? X is, because x is this, y equals x, right? And exponential at first is growing faster, but then it tapers out. It keeps going up forever. It doesn't have a horizontal asymptote, but it just gets less and less steep. So that one's going to go to infinity. 3 to the x over 2 to the x. Well, both of these are exponentials, but the bigger base is going to outgrow the smaller base, so that's going to go to infinity. So just knowing how these functions relate to each other can help you get the answers quickly so that you don't have to do like L'Hopital's rule and stuff. I mean, you could if you want, but 13, the graph of which function has y equals -1 as an asymptote. Well, that means if you want to find asymptote, take the limit as x goes to positive or negative infinity. Positive or negative infinity, because you might get two different asymptotes, one direction or the other. They might be the same. You might only get an asymptote on one side. So here, if we do, this is the same thing as 1 over e to the x. If you go to infinity, that's going to go to 0. If you go to negative infinity, you're going to get, it's going to blow up because it's going to be negative infinity, so it's going to be e to the positive infinity. So it's not that one. This one, we'll go to infinity. These are the dominant terms. So it's going to be negative 1 over -1, which is positive 1. If you go to negative infinity, you get positive 1 over positive 1, which is also positive 1. So that one's not it. This one just, if you go to infinity, it blows up. And you can't go negative infinity because it's not in the domain of natural log. You can't take natural logs of negatives. This one is going to be 1 over 1. This is the dominant term. So it's going to be 1. If you go to negative infinity, it's going to be -1 over -1, which is 1. So it's not that one. This one, we're going to use the dominant terms. So it's going to be 1 over -1, which is -1, or -1 over +1 if you go to negative infinity. That's the one that has that asymptote. Just remember with asymptotes, you got to check not just infinity, but negative infinity also. Number 14, y equals 7 is a horizontal asymptote of a rational function f. Then which of the following must be true if it's the horizontal asymptote of the function f? That means as we go to infinity, the function goes to 7. Right? Or negative infinity, which isn't an option here. But that could have been the correct answer. Either one of these would be the answer. Not as you go to 0, not as you go to 7. If you go to negative infinity, it's got to go to positive 7, as far as what they said. Right? Okay, let's take a look at the next page. Try a couple more of these. You guys are going to try 16 and 18. So try 16 and 18. Pause the video. And then try them and unpause it. We'll talk about them. Which of the following graphs best resembles this function? Well, some things we could figure out is that vertical asymptotes are when we get division by 0. So that's going to be when absolute value of x equals 0. Well, that's going to be absolute value of x equals 1. So that's going to be x equals plus or minus 1. So we're looking for one that has two vertical asymptotes, a -1, +1. This one's out. Those other ones have it. How about, let's look at horizontal asymptotes. As you go to infinity, these are dominant terms. And as you go to positive infinity, it's going to go to 1. And as you go negative infinity, it's going to go to 1. So both sides should go to positive 1. Right? That one works. That one works. This one's going to -1. This one's true. This one's going to +1, -1. Right? Now, what's happening in the middle? Just plug 0 in. You get -1. So we need 1 that's at -1. So that one's out now. And then let's plug values bigger than 1 in and see if they give you like negative values or values less than 1. If you plug like say 1.5 in, you get 2.5 over -0.5 is a negative, which is over here. This one can't be it. So it's got to be E. Or I don't know. Hold on a second. Shoot. Let's see. If we plug, wait a minute. If we plug 1.5 in, we get 2.5, and you plug 1.5 in, and you get 0.5. That's positive. So I think it's actually this one, not that one. If you plug anything bigger than 1 in, then this is going to be positive, right? So it's got to be this one. Okay, 18, the graph has no horizontal and one vertical asymptote, one horizontal and one vertical asymptote, two horizontal, one vertical. Well, let's figure it out. If this equals 0, that might be a vertical asymptote, right? So that's going to be absolute value of x equals 1, x equals plus or minus 1. So I feel like it has 2 vertical asymptotes. So it's got to be one of these. A, B, and C are out. Horizontal asymptotes is we take the limit as x goes to infinity of x over 1 minus absolute value of x. It's going to go to infinity over negative infinity, so that's going to be negative 1. Let's check the other side. Now, if the other side is the same, then it just has 1 horizontal asymptote. If the other side is a different horizontal asymptote, then it has 2 horizontal asymptotes. So if we go to negative infinity, what's going to happen? Well, the top is going to go to negative infinity. The bottom is going to go to negative infinity, but you take the absolute value of it, which makes it positive, and then there's another negative. So it's a negative over a negative. It's going to be positive 1. So it actually has 2 horizontal asymptotes. 2 horizontal, 2 vertical. Okay? Now, I'm going to save the rest for you guys to try, and then I'll put my answers and work up on later, and you can check them, fix them. The solutions should be up already, so you can just see if you got the right letter, and then the work will come up later. But this is some good stuff.